In this video, I'm going to show you how you can inspect your circuit breaker panel, make sure everything is properly wired, and I'm also going to point out a few problems that can occur with these panels and how you can correct those problems. The panel that you're looking at here is a single-phase residential panel. It's rated at 100 amps. You can see you have two lugs. That's a hot line coming in. That's your other hot line coming in. If this was a three-phase panel, you would see not just that hot lug and not just that one. You would have a third one. Each one of these is 120 volt potential. So between that lug and the neutral or ground, which is right here, you have 120 volts. And from this lug here to that terminal, you also have 120 volts. Between the two together, you would have 240 volts. Now the first thing you want to do when you look at the panels, you want to observe the wire sizes in relation to the current rating of the breaker. If you have a 15 amp breaker, you want to make sure that the wire attached to that breaker, whether it's stranded copper or solid copper, is going to be 14 gauge copper. If you're using aluminum, aluminum has higher resistance than copper. You're going to want to use the next wire size thicker to compensate for the difference in resistance. For a 15 amp breaker, instead of using 14 gauge copper, you would be using 12 gauge aluminum. Now if the circuit breaker is rated for 20 amps, you're going to want to make sure that the wire is a 12 gauge solid copper or stranded wire, or a 10 gauge aluminum. If you have a 30 amp breaker, you're going to want to make sure that the wire connected to that breaker is a 10 gauge copper or a 8 gauge aluminum. If you have a 40 amp breaker, you're going to want to make sure that the copper wire attached to that breaker is an 8 gauge wire or a 6 gauge aluminum. If you have a 55 amp breaker, usually that goes to a stove or a central air unit, as well as other appliances, that would demand a 6 gauge copper wire or a 4 gauge aluminum. If you have a 70 amp breaker, you're going to want to make sure that you have a 4 gauge wire in copper attached to that breaker, or a 3 gauge or a 2 gauge aluminum wire. If you do have a 70 amp breaker and it's feeding a sub-panel, because it's not being used as a service entrance conductor like you see here, this 4 gauge wire, because it's a service entrance conductor going into the panel from the utility, you're allowed to use a 4 gauge wire for 100. If you wanted to go to 110 amps, you would use a 3 gauge copper wire. If you wanted 125 amps, you would use a 2 gauge wire going into there. If you wanted 150 amps, you would use a 1 gauge wire. If you want 175 amps, you would use a 1/0 wire, which is a 1/0, or if you wanted to use a 200 amp service, you would have a 2/0 wire. Then it goes 225 amp, you would use a 3/0, and you'd have a 4/0 wire for a 250 amp service. And as I said earlier, you would use the next size thicker or the next size heavier wire in aluminum if you were going to do so. Now the neutral wire, which is right here, you could touch that one, believe it or not. All right, power on. This is connected to the ground. On the utility pole, on the transformer, or on your pad mounted transformer, you have your 3 terminals. The 2 outer ones are 120 volts each. The 2 together make 240. From the outer connection to the center would be the 0 volt connection, which is the neutral. That's 120 volts. And the outer connection on the transformer to the inner on the left side, you would also have 120. So this is 0 volts potential. On the power transformer, this connection here, which is the middle screw on the transformer, is also connected to earth ground. You'll see a wire running from that post on the transformer heading straight into the earth where it's connected into a copper rod. Now when these panels are connected up, there's 2 ways that they do it. Your neutral wire coming in, which is usually the same size as your hot feeds, or it could be one size smaller. There's not a problem there. So as long as you see that these are properly rated, and if that's one size less, you're okay. So if this was a 200 amp panel, you would want to read the writing on this copper wire. If it's copper, make sure it says 2/0 which means 2-aught, then you know you have the right size wire for the panel. That wire is capable of handling 200 amps as a service conductor. And then you might see that the neutral or the white wire, these are always white or gray. This may be a 1-aught copper. There's nothing wrong with that. So if you see one that's a little smaller for the neutral, you're fine with that. Now there's two ways the neutral is connected in the panel. Either it's isolated like you see here, or it's connected to the enclosure. Now in order to connect this to the enclosure, which would basically be the ground, just like on the utility pole how it's grounded, there's two holes. Through those two holes there is a threaded hole on the enclosure. You would place a bolt right there. You would tighten it in securely, and what you would be doing is you would take the neutral and you'd be bonding it to the panel, making the panel also neutral. When that is done, you normally would take all your white wires, which is your neutrals or your grays, and your bare wires or your green wires, and they all would be connected to these terminals you're looking at right here. If you choose to not bond the panel by placing the screw in here and tightening it down securely, then the next thing you would do is you would have a separate ground wire, usually a 10 gauge wire, could be a little thicker. In this case, whoever put this panel in didn't have the right color wire, so they took two 14 gauge wires, twisted them together, and it connects right here. It's screwed into the metal enclosure. This wire right here, which is connected to this lug, goes through this cable, and it goes outside the house where it goes onto a clamp on your cold water pipe, or it gets clamped onto a copper rod or a copper clad rod, which is driven into the earth. That makes this whole panel grounded. You would have your separate ground bars, which you can see right here. So all of your bare wires and your green wires should all be connected to these bars here. There's one on both sides. And then all your white wires will be connected to the neutral bar. You want to make sure that's properly done. Now for code reasons, and it does vary depending on local building codes, they do not like to see splices performed inside your breaker panel. You also want to make sure that every single screw on every breaker has only one wire per screw. Now a lot of breakers, I'll take this one out and show you. Just pop it out gently. Alright. Pull it hard like that. Let me take this one off altogether. Show you closer. Alright. If you look inside the breaker, you're going to see there's actually two places to put a wire. You can put one on that side or on that side. So even though it's designed to hold two wires, they only want you to have one wire in that connection. So make sure when the wire is stripped, you strip off about 1/2 inch. Make sure it goes all the way in. You also have to be careful that when this is tightened down, that you don't have part of the insulation in between the contacts. Because when you go to tighten this down securely, if it's not just bare copper in there, you're going to have a very bad connection, if any connection at all. So make sure you check those. Put this back. Tighten it down securely. I'm going to leave this one out because I'm going to want to show you the bus bars in a minute. You're going to want to check every single one of these screws on all these breakers. Make sure it's very secure. Turn off each breaker as you check each screw. When you're done checking each screw, turn it back on. You don't want to do it while it's on, even though I do it that way, because there's always a chance you might forget and your finger might come in contact with the blade of the screwdriver and you can get a very painful or even a lethal shock. So make sure you turn the breaker off. Once you made sure all the screws are tight and you also made sure that all of these wires are the correct wires for the ampacity of each breaker, we can go on to another step. Now, a problem that's fairly common, especially in a lot of Challenger panels that were made back in the 80s and 90s, and there are some other companies as well. I would have people call me up for service calls, and I would get to their house and they'd say my hot water heater's not working, or my air conditioner's not working, and I would take a voltage reading. Now, the tools you're going to want to use are a digital multimeter. You can also use a bar meter. This has a solenoid. When you take out the two connections, you can put them like this. Alright. The bar meter is very simple to use. It Take one probe on one connection and you can go to ground. Alright, you can see 120 and the neon lamp glowing. You go to 240. It jumped over to 240. You saw the neon lamp is brighter, dimmer, brighter. Another useful tool is a clamp-on meter for measuring current. This goes up to 600 amps. And what this is good for, I would turn that on. This clamps right around your wire, like that, and then you'll be able to measure how much current is flowing through the wires. When you set up a breaker panel like this, you put all your 240 volt breakers in. Those are fine. When you put in your 120 volt breakers, you want to make sure that you have a balanced load on the panel, and that's where this would come in very handy. You would have everything running like it would normally be running, and then you could take a measurement with your air conditioning going or anything else and compare the readings on the two wires. You want to have them very close in the amount of load on each one. You don't want to have one with 80 amps and one with 20, so you would want to balance things out. This is also very useful for measuring the current flowing through wires. If I wanted to check the water heater current, I could do it from here as well. Very handy tool. Another useful thing to have is this infrared thermometer, and I'm going to show you why right now. So once they called me up and they had no power going to the water heater, some people actually had 240 volts at the water heater. The problem was once the load was turned on, then the 240 volts disappeared. Now if you're having a problem where you're not getting full power to your hot water heater or any other appliance, your air condition, you're going to want to pop out the breaker that the air condition's on or the hot water heater. You're going to want to inspect the clip. You're going to want to look very closely at the clip, see if there's any burned marks or if it's pitted up. And if you find one where you notice that this looks a little burned, what's going to happen, let me take the camera a little closer and show you. Alright, right there is a bus bar. You can see this one here is separate from that one over there. This one goes all the way up to that lug, and that lug there goes all the way down and ties into that one right there you're looking at that connects that way. They alternate. There's one from that lug going this way, and there's one from this lug going that way. The next one up will be coming from this way. So when you want to have 240 volts applied to a circuit, you have to make sure the circuit breaker is clipped into each lug. So you're going to want to look at that connection right there. And a lot of the time I have seen in the past that when this clip here is burned or pitted, you're going to see the same thing on the bus bar. After disconnecting the main power, this panel here does not have the main breaker inside the enclosure. It's separate. It's located over here as a throw switch. Yours might be in a separate housing like this, or it may be at the top. If it is, make sure you shut the main breaker off to turn off all power to all the other branch circuits before you go anywhere near these connections to clean them. If you have a lot of spaces where the bus bars are perfect, then it would be a good idea to abandon where it's actually burned and pitted and move this breaker to a new location where it's not pitted. If you don't have a spot that's not pitted, then you're going to have to clean that very carefully. Take a small file, a flat file, flatten it out. You're going to want to take a stainless wire brush, go in there and clean that. Once again, make sure the power's off. And then you're also going to want to get the breaker and clean the clip. I also, after cleaning everything, I like to put a compound called No-Alox. It prevents aluminum oxidation. It works extremely well between aluminum and aluminum connections and aluminum and copper connections. Brush a little bit on here, and if you want, you can also take a needle nose and you can squeeze this a little tighter. And I would actually suggest you doing that. By making this tighter, don't overdo it, just make it a little tighter. It'll make a better connection when you pop it back into the panel. You want to make sure that these connections here are also very clean. If your panel is being fed from a main breaker in a different location, shut the breaker off or pull the throw switch, and then you could unscrew these. You could take a wire brush, clean the copper, clean out the lugs. You can brush some No-Alox on the wire, reinstall it in, and tighten it down securely. Now the reason why I like this infrared thermometer is because I could take a look at connections while the power's on to see if they're generating any heat due to high resistance connections or corrosion. So I would point this at this lug at close range within a few inches. It's 89. And it's around 89 as well. If one of these came out at like 100 or 110, you're going to know that this connection here should be unscrewed and definitely cleaned and put back together. It's normal for circuit breakers to run warm if you're running especially near the full rating of the breaker or close to it. It's not normal if the breakers are hot. If the breakers are getting hot, that would more than likely indicate, like I said earlier, that this clip is probably very corroded and it's a high resistance connection and the current is heating up the whole breaker as well as the bus bar. So you're going to want to check that out. So you can see 89, 89, everything's the same, that's fine. Alright, so now you know about checking the bus bars out, making sure there's no corrosion between the breaker and the bus bar. If there is, to clean it, make this a little tighter. If you have a space, move it to a different spot. If not, clean that spot and reinstall. You know to check the lugs, make sure they're tight. You're going to also look around, make sure you don't see anything that looks burned. You could take a Phillips screwdriver on any of the neutral bars while power's on. Tighten these screws down securely. Check that screw there. Make sure that this bar with all these terminals is securely fastened to the top neutral bar. You don't want anything loose. Every single wire attached to your breakers must be a red, black, blue, yellow, orange, any of those colors. You don't want to see any whites, you don't want to see any grays. If you see white or gray on here, make sure you wrap it like you see here with black electric tape. This way it's marked as hot. This breaker I could pop back in. Let me just make sure it's tight. Make sure it's off before you pop it back in. Okay, push this like that. Double check it again, make sure. Then I can throw that back on. Adding a line is very simple. You want to add another 15 amp line to your house. Pop in a 15 amp breaker on one of your bus bars. Take your 14 gauge wire, connect it. Take the neutral, the white, connect it to the neutral bus. And then you take the ground and connect it to the ground bar. And you're good to go to send that to a branch circuit. Now when you test the 240 volt breaker, my meter I set to 750, 1000. Make sure it's on alternating current. It's not a good idea to test on a 240 breaker from there, from one pole to ground. Or I can go to neutral in this case, alright? So I got 120. Because if you do that and there's a problem with the breaker, you're going to have a loop back. So the one leg will feed through the circuit and come back, and it won't connect to the other bus. So you're going to see 120 and 120. So I'll do this, alright? So you see there's 120. And I'll do the one above it. And you'll have 120. That's not how you test a 240 volt breaker. So when you check a 240 volt circuit, you always want to check between both screws. And I have 240, alright? That's how you want to check those. If this was a hot water heater circuit, or an air conditioned circuit, or a range, and you think you're having a problem with power at the range, you could leave the two probes connected. One there, and that one there, alright? And while it's connected, you would turn on the load. It's normal to have a little bit of a voltage drop, but if you see that 240 go down to 100 and something, you're going to know there's a problem with either the breaker or the clip where it clips onto your bus bars, and you should check it out. Now the breaker you're looking at right here, the GFCI, this has a self-test on it, alright? You push that button to test it. You can also test it without pushing that button. You could have one wire going to either the ground bar or your neutral, and then you could touch the screw. It should trip. Alright, it works perfect. Now the reason why it tripped is because it's simulating exactly what this button's doing. The current that left on this black wire must return on the neutral wire going into this breaker. The breaker monitors the current leaving and coming back. If somewhere in this circuit, it could be you with your hand touching a bare wire, if you touch that hot wire, you're going to create another path for the electricity to flow, and when you do that, it's not going to be flowing through the breaker. This is going to recognize that there's more current leaving on the black wire than there is returning on the white, and it's going to cause the breaker to trip. And the amount of current is extremely low when this trips. It may be 1 milliamp, something very, very small, where this will save your life. And that's the purpose of the GFCI. You are pretty much set. Now I also have on this panel, you can't see it, I'll tilt up just a little bit, right at the top right there, that is a surge arrestor. If there's a surge coming to the power supply into this house. Now what's inside there is a component called a varistor. Varistors are designed that when voltage is kept below a certain level, the resistance of that component is extremely high. As the voltage climbs, as in a surge, maybe 275, 300 volts or higher, what will happen, instead of everything experiencing that surge, the surge arrestor more or less acts as like a shock absorber. It takes that pressure, which is actually higher voltage, and it suppresses it. The resistance of the varistors begins to drop, and as it drops, it allows the excess voltage to be shorted out to prevent the excess voltage from going through the branch circuits into your house. Now they work extremely well, but they're only designed to work for a very brief surge, milliseconds or microseconds. Anything more than that, the surge arrestor is going to fail and you will have damage in your home. So they help, but they're not 100% guarantee. Hopefully in this video I explained a lot of things to you with regards to your circuit breaker panel, how things work, what's proper, what's not proper, and certain things you could do to correct things, as well as how to properly test the voltages on your panel. If you enjoyed this video, please rate it a thumbs up, subscribe, and post links to this video on other websites and blogs. Also be sure to check out my video playlist as well. Thank you very much for watching.